a 30-minute introduction to data analysis. This is largely oriented for those of you who might be more new to programming and thinking about how you might set up data analysis pipelines. But I wanted to start with just a brief personal introduction because I've spoken a couple of times, but haven't talked at all about what I do. So I want to put that into context because that influences how I think about data analysis. So for those of you who might be around later today, we'll do a tour of my lab. So I direct the locomotor control lab here, which is downstairs. And so I'm an engineer who did a postdoc in neuroscience, who's now in the physical therapy department. And that basically covers the range of what we do in the lab. So we do a lot of work that all of our work really focuses on various aspects of mobility in different populations, really big into just considering how factors like energy costs or effort and stability or balance influence how we move, how those factors change after something like a stroke, and then how we can use that knowledge to ideally improve the content of physical therapy. So just to give you sort of an overview of methods, which again help you get a sense of how I think about data analysis. We do lots of motion capture in the lab. So we do full body motion capture, many markers. So that's sort of big data on a small scale because we have 100 measurements per marker for 50 markers for many minutes. We use tools like biofeedback. So we write code in that case to give people feedback about how they're performing. And we do a lot of studies that look at balance control by generating what we might call simulated slips or trips on our treadmill to understand both what we call neuromechanics, so both the neural control of balance and how that neural control interacts with the biomechanics of the body. We also look at mechanics using things like musculoskeletal models, where we use models as a way to test or generate hypotheses, really. We might simulate a type of impairment and then look at how that impairment changes performance, similar to something what Joe mentioned last night, where we're again thinking about things like energy cost and how that might relate to aspects of walking like gait symmetry. And then finally, we do a decent amount of work using virtual reality as a way both to study skill learning and to perform assessments and interventions for mobility. So that's a little bit of the context of the work that I do. And so I wanted to talk today about data analysis from this perspective. This was a statement that I heard from somebody who shall not be named when a student was presenting essentially something like their qualifying exam. So it was a proposal about future research. And this person said, I'm sorry, but you're really dealing with a house of cards. And so can somebody tell me what's the key feature of a house of cards? The key problem with a house of cards? Instability, right? So if all the cards are precisely placed, it's beautiful, it can be beautiful, really wonderful structure here. But if one of those pieces is moved slightly, right, everything falls apart. And that was essentially the statement being made. And the reason for that is related to a lot of these things that we've said, right? We and I have done this myself, sort of built a story in our minds based on lots of very weak evidence. And if one of those pieces of evidence isn't true, then it's likely that the study we go out to perform will yield results that are not statistically significant, or it won't work because our fundamental premises are wrong. So even though we're talking about data analysis here, I always like to highlight this issue of one of the first things we all do, right, is select a research question. We haven't really talked much about that. I like this figure from the textbook Foundations of Clinical Research, which sort of highlights a lot of the steps that go into selecting a research question and identifying your research objectives. And so ideally, you've done a lot of background work to really identify a really strong research question. And the way that I introduce this objective to the students and postdocs in the lab is, okay, there's some world of really important questions, and most of us are in rehab, so we are drawn to important questions that matter to people's daily lives. And then there's some space of answerable questions, right? So not all important questions are, I would say, currently answerable given the tools that we have at our disposal. And then there is a smaller set of questions that you can answer with the tools and skills that you have. And you're really looking for this sort of little space, which I guess you can all see. Laser pointer here, right? So this is kind of the space where you ideally like to. I want an important question that's answerable and that I can personally answer, right? And so that's really how you want to think. I say that you want to think about setting up your career. So before we even talk about data analysis, we want to, it depends on how we design our experiments. This paper is one of my favorite papers. I introduce this to my experimental methods class every year. And it's a really great, provides a really great framework for as you're thinking about designing a study or identifying a research question. It just gives you a list of questions that you need to answer that talk through things from instrumentation, the experimental design, statistics, data collection, analysis, and so on. And I think it's really wonderful way to make sure that you're crossing all your T's and dotting all your I's in study design. Okay, so let's assume that you've already designed a really strong study. I think maybe, I don't know, Keith, did you show this yesterday?
No, not this one.
Oh, cool, okay. So this is a figure that I really like. And often when we think about issues related to, let's say, I'll say irreproducibility, we often think a lot about, statistical factors that go into our p-value, right? Statistical power, your sample size, p-hacking, how many hypotheses you're testing, and so on. But this is sort of the end of the data analysis pipeline. And often we sort of miss the focus on these earlier stages, which I consider to be part of your pipeline. And that's starting with experimental design down here. You've heard a little bit about documentation in different domains throughout the weekend. We won't talk about that a lot today, but you want to document all of these things from the sources of information you use to identify your research question through your statistics. Okay, so what we're going to do for the next 20 minutes here. So I have just a general outline of the data analysis pipeline that at least I use and introduce to my students. I'll try to save 5 to 10 minutes at the end to do a hands-on example. This is going to be in MATLAB. Sorry to everybody else. You got to deal with it. But here are the steps, right? So before you do anything, you need to know your data. We'll talk about what that means. You need to know what you're trying to do. This is going to be one of the harder steps, I think, often for people who are sort of new to what we might call data science or signal processing or whatever you want to call it. And so you do this stuff before you even open whatever your programming environment of choice is. So you get your data into your environment. You do some quality control. This is highlighted, or there's an asterisk here. I use data, you want to use data visualization and different forms of data visualization every step through the process to make sure that your code is doing what you want it to do. You can do some pre-processing, maybe compute some summary measures, create figures, form stats, and save your results, and submit your paper. So I like to try to do this, all in the same environment. Someone mentioned yesterday, realizing that they could do statistics in MATLAB. So I actually do a lot of stats within MATLAB. And I like to have pipelines in my lab that do all these things using some modular code, as you were also introduced to that idea yesterday. So we'll show an example of this later today, or this morning. Okay, so these are some basic things about knowing your data. So I deal with a lot of signals, so time varying measurements like marker positions, forces, EMG, accelerometers, whatever it might be. So that's how when I think about data, that's generally what I'm thinking about. And so things that become really important are sample rates. If you have many different sources of information, those sample rates might not match, so you need to keep that in mind. How are you going to deal with that? Units of measure, I talk about this all the time with my students, because once you get a signal in MATLAB or whatever environment, the units are gone. And if you don't know your units, right, if you don't write them down, put them in your script, it's really easy to compute things that make no sense, right? And we can talk about all sorts of cases where that's happening here as well. And the fourth point, which I don't think we've really touched on this weekend, is really when we think about our measurements, we actually need to understand how accurate and reliable they are. So this is a major place that can, or issue that can influence the reproducibility of our results. So we can think about our measurements. We can think about several different sources of error in our measurements, right? There's this idea of intra-rater reliability. If I make the same measurement multiple times, how consistent is that measurement? So we can reduce that source of error by having people be well trained. The measurement instruments we use are really important, right? So those of you who might care about accelerometry, right? We all carry around an accelerometer, and you can literally write code to record this data on your phone. But you need to understand something about how accurate those measurements are. And then there are some measurements that just change naturally with time. So these might not necessarily be errors, but they are sources of variability that will influence your ability to detect differences if that's what you're trying to do. So you really need to know your measurement instruments. Then you need to think about, okay, what are my data? So this gets into more what you might think about with data analysis. What format do I store my data? Am I bringing in data with different formats and sample rates and so on? And then you want to make sure you spend some time understanding how all those files are organized. And again, so we're going to do an example of this in just a few minutes. So it's really nice that you want to make sure you have all of this information both in your head, but also written ideally in your scripts or in things like README files that you might include in the folders where you store your data. So, lots of different potential file types and formats. We won't talk about the differences between these, but just recognize that it's important to know what you can and cannot import into different analytical environments. Okay, so now you're at the point where you really want to make sure you know what you're trying to do, and this might seem trivial, but this is where for people who are new to, again, more of the sort of data sciencey things, where things get a little tricky. So these are just sort of general problem solving steps, right? So we have some question. We want to make sure that question is stated precisely so that we can know if we've answered it. Generally, we're going to start with, what is it that we already know? A key thing for people who are new to science is how do you actually know when you answered your questions? Sometimes if you don't state that really precisely, you can go down an analysis path where you get some result, some answer, or some analysis, but it might not actually match the question. So at that point, you need to write out your procedure for answering your question. And so I have a few points here that I've added this morning based on yesterday's discussion. Right, so there's one major step where we can argue about the utility of AI. And I'll just put a stake in the sand here where I think AI is really useful at this step. Right? Here are my data, here's what I'm trying to understand. What is a step-by-step procedure by which I could process my data to answer this question? So we're not generating code at this point, but we're generating a step-by-step solution to this problem. Once you have that and your steps are really, really clear, you can argue again about AI. So now, if your steps are clear, you're going to be much more likely to get usable code if you ask ChatGPT or whatever you like to generate that code. Okay? But I think doing 4 first is really critical here. So this is, I won't read through these, you'll have the slides later, but these are sort of common individual operations that you might include in this fifth step here. Okay. We're good on time. So just so you know, I said I teach a class on experimental methods for studying human movement. So this is like a 30-minute version of things that I teach in an expanded way over several weeks. So this is a little challenging. All right, so basic programming principles. If you're new to programming, these are really critical. If you're very experienced, hopefully you're already doing a lot of this. It can be very tempting to try to write your program, from start to finish all at once, as if you're, writing a paper or something like that. This is a major place where people run into problems. So you really want to break down your programs into, again, simple steps, check each step, use data visualization to check the accuracy of what you've done, save it, and then move forward. So I'm not going to talk about using version control here, but this is where version control is really helpful. The most basic form of version control is save the version of your file that works, save it as a new name, _1, whatever, and then start working on that second file. Right? And again, the point is that you don't want to lose the thing that works in case one of your future updates or modifications, quote unquote, that your code. For people that are new to programming, this is the most annoying thing in programming, right? If you're in a biology class and you want to memorize the Krebs cycle, you just have a list of what those steps are, and you use flashcards, or I don't know what people do these days, use an app or something. You don't get a lot of negative feedback as you're studying. With programming, you almost only get negative feedback when you're starting out, and you get these weird sounds from whatever language you're using that tell you there's an error. That can be really frustrating. But that's the error. Those errors are really helpful. And the messages that you get, even though they seem like they're written in a foreign language, are really meant to help you fix your program. So you really need to spend some time making sure you can decipher the error messages you get or whatever language you're using. Again, we're in the world of AI. So now, whereas a year ago, I would say, copy the message and Google it, you just put it in whatever language or large language model. And, those large language models can be very helpful for helping you decode your errors. Okay. Another basic principle, the absence of errors messages does not guarantee the absence of errors. This is a common problem when people are starting out with programming. Here's some MATLAB code where I want to look at how the scores on a test change across sessions in some classroom. I run this code, I get no error messages, and I get a figure like this. Like, oh, the scores just go up linearly with session number. Anytime you get data that looks like this, there's probably a problem. If it looks too good to be true, it probably is. So here, very simple problem. I have X represented twice here, right? I should be X and then Y. But I have to be able to make sense of that figure and understand that it's not what I expect. I correct my error, and then I get something that looks like this. So this is, I don't know, literally everybody does this. I have this conversation almost weekly. It is very, very, what we're all, everybody in this room is tuned to look at a figure and then create a story that fits with the figure they just saw. It is, I don't know what it is about human nature that makes us do this. We like to understand things. I think, like uncertainty, but you always want to be asking yourself, what did I expect to see? Does what I see match what I expected? If it does, that still doesn't mean it's right, right? You always want to go back and check the validity of your pipelines. The last thing here, so these 3 C's of programming. So I'm citing a textbook that I really like, written by a psychologist who was formerly at Penn State. Be very clear at comments to your code. You've heard that time and time again over the weekend. I have this in bold. Writing a longer variable name doesn't cost you anything. Using something like X You will hate yourself. 8 months later, and you get the reviews back from your paper. You're like, what did I mean? Just use a word. It doesn't cost you anything. Be concise. Won't talk about writing functions, but get something that works first. And then again, we can argue about the use of AI. JB mentioned this yesterday. AI can be helpful for taking a set of code that works and then making that code more precise and making it modular. And then obviously things need to be correct. So this is, I think, the last slide before we rapidly do a demo. So when you're writing your code, you want to think about your audience. Mostly we think about the computer, right? I'm writing code and I want to make sure it works and gives me what I expect. So that's sort of like written for the computer. So that's very basic. You also often, we talk about the whole, we're really talking about reproducibility, open science, and things that you want to share. So you want to think about the scientific community also as you're writing your code and your lab mates, so that what you write is readable by somebody other than yourself. And then we've already talked about this over the weekend. You know, I write code today. I get feedback on my paper in July. I need to make sure that I can interpret the code that I wrote a year ago if I need to make changes. All right, so we're going to do a quick demo here. Two things. One, this is going to be in MATLAB. You don't need to open MATLAB, but this is an openly available data set. We're talking open science. I use this data set in class. I really like it. This is basically a study where they had 10 participants walk on a treadmill. They measured lower extremity biomechanics bilaterally. And they had 3 different testing conditions. A kind of baseline condition where they just walked normally, a condition where the participants wore a knee brace, and then a condition where they wore an ankle brace. So I like it because this is the type of intervention that's likely going to have a really large effect size. And so it's a really great way to easily write an analysis pipeline that allows us to test a set of hypotheses. If you go to this website, they do a really great job of describing the data set, the coding for various variables, whether it's condition, participant number, leg, joints. They're all coded with numeric values, a simple CSV file that you can download. This is a second, it looks like the same. This is a second QR code. If you just want to download the data, and this is going to be one M file that we're going to use, you can go to this. It should take you to a Google Drive folder where you can download, like I said, just a CSV file and an M file. So get people. So I wanted to just demonstrate a couple of things in MATLAB. One is, again, this is my personal style, but also show you how I might go about starting a script, which, as I've learned in teaching my class, is one of the hardest things for people who are new to programming. Like, what do I write first? I'll also show a little demo for those of you who don't know or don't use MATLAB. This year's version of MATLAB now has Copilot built in. So as you're writing a script, it can generate code for you, which is something that's very new for me. And I'll show you how I tried to make it more useful. And then we'll run through the script that you all can download that does all the processing. So you can just see an analysis script. Okay, so I'm going to flip over to that. All right. Okay, so the file that we have is called gate.csv, and I can open it really quickly from MATLAB by just clicking. Oh, thank you. Again, we don't have time to make sure everybody can follow along on their computer, so don't worry too much about that. But I think the first step I always say is to know your data. So I take this CSV file, I can choose open outside MATLAB. This will open in Excel, and I can just start to get the gist of the data set, right? So I have, again, general good practice with structuring CSV files. First row is a header containing human readable names for my variables, no spaces in the variable names, very basic stuff. If I scroll down, I can see that this data set sort of goes forever. Something like 14,000 lines of data, 14,000 measurements. I would never want to manually look at this. There's no reason. But at least I know what each column represents. And I've taken the naming schema from the website. So then I might go into my editor where I can start to write code. Here, I actually this. So I've just pasted the data naming schema because that's going to be useful later on, both so that I can know what to put in the code, and it's also useful for MATLAB if I want to use the AI generator. So I like to write each step as a comment. When I do this in class, I actually just write all the comments, like the steps by which I want to do my data analysis. I write the comments all first. So then you can go back and fill in the code. So here's an example of what the world of programming in the world of AI, I guess, looks like. So this comment, I've written this both for me and for MATLAB. I'm going to load, I give it the exact file name, I tell it which function I want to use, read table, and then I tell it what kind of variable, the name of the variable that I want to create when I import the data. If I just press enter, MATLAB generates some example code. Turns out this first line of code is correct. So it creates the variable read data using read table. And sorry, let me delete this. It's actually trying to do everything else. All right. I'm going to press tab. There's my first line of code. I then, because I know, so it's trying to guess what I want to do next. It's often, almost always wrong. I just ignore this. I'm going to paste the comment that I just had. Okay, I want to extract the ankle joint angle for participant one, condition one, replication one for the right leg. So it's possible, if this AI is really intelligent, that it's going to take this information up here and use it to generate the next line of code. And so in this case, it's almost correct. So the key problem here is that the variable names, even though they're specified up here, it's using capital letters here, which isn't correct. But it at least gives you a sense of the kind of code you might want to generate. So to finish up, the code that you downloaded is a complete version of the code. We wrote this over several weeks in my class, but it's going to go through, load data for each person, for each condition, look at a particular joint angle, compute the range of motion, store average over 10 cycles, and then save the result, make a figure. So it's 63 lines, but it's mostly comments. It's really about only lines of code. Okay, press run. if this were my own project, right, I might, as Devin mentioned yesterday, right, I might actually separate the data importing into its own function, run that once, save the result, and then have an analysis script that just loads that. But here we were testing the hypothesis that adding wearing a knee brace reduces the knee's range of motion. And so I'm just showing the knee range of motion on the y-axis. I've written code to label each condition on the x-axis, and it's really obvious that the range of motion is much smaller in wearing a knee brace versus the other two conditions. But there, one interesting finding is that it looks like, again, this is visual stats, wearing a knee brace might actually change the range of motion of the ankle. Maybe unsurprising. So that's data analysis in a nutshell. I think I'm out of time. Feel free to take a look at the code, and happy to answer any questions. I think we have another almost 30 minutes here. Yes.
I have a quick question. What like button or